So let's go back to example 1 here and apply some of what we have learned. So since our n, our sample size, is 125 here, and that's certainly greater than 30, the central limit theorem, we're abbreviating that CLT, tells us that our sampling distribution, our x-bar distribution, is approximately normal. And we want to know what percentage of weights should be within 1.96 standard deviations of the population mean. So that's saying that here's our sampling distribution, and remember that the mean of that distribution is mu sub x bar, which is also equal to mu. And then we are going to add 1.96 standard deviations right here. So this is going to be the population mean plus 1.96 standard deviations of that sampling distribution. And then right here is that population mean minus 1.96 standard deviations of the sampling distribution. And then what we saw up above was that this is 95% of the data. Okay, so that was the inverse norm calculation. We had 97.5% to the left. So, and that left us 2.5% of the samples out here and 2.5% out here. So remember what this means is that for 95% of the samples, if you generate the interval from that mean, it's going to contain this mu, this population mean. So what is going to be the standard error of this x-bar distribution? That is, what is this piece here, the sigma x-bar for the sample means? Well, let's suppose that our population standard deviation is 5.2. So I'm giving you some more information here. Then our standard deviation of the x-bar distribution by the central limit theorem, that is sigma divided by square root of n. So that was one of our properties of the sampling distribution. And what's our sigma? It's 5.2. And our sample size is 125 right here. And so we're dividing by root 125. And let's go ahead and compute that. So we have got our 5.2 divided by square root 125. So 0.4651. So there's our standard deviation of the sampling distribution. And then what we know is that we know for 95% of random samples of size 25 with this standard deviation of the population being 5.2, that x-bar value is going to be between the mean minus 1.96 standard deviations and the mean plus 1.96 standard deviations. So for 95% of the sample mean values, those x-bar values are going to fall in here. But remember, we rearranged this and said, well, that's equivalent by algebra to saying that the population mean is between x-bar plus 1.96 and x-bar minus 1.96 for 95% of all random samples. Well, this value here is called the lower bound, and this value here is called the upper bound of our interval estimate. So let's go ahead and compute those lower and upper bounds. So first, 1.96 times our standard deviation, sigma x bar, which is 0.4651. Let's compute that. That's called the margin of error. And so we've got 1.96 times 0.4651. So 0.9116. And we've got, let's use a couple decimal places here, 0.91. So 0.91. And then what we're going to do is we're going to take our population mean and subtract that and add it. So our lower bound, and I'll abbreviate that, LB, is going to be let's see, our x bar minus the 1.96 standard deviations. And our sample mean, that was 195.4. If we look back up to that example, so we took that random sample of size 125, got 195.4. We're going to subtract off 0.91. That'll be our lower bound. So 195.4 minus 0.91, 194.49. And then we're going to find the upper bound. I'll abbreviate that UB. That's right here. So that's the sample mean plus 1.96 standard deviations of the x-bar distribution. So that's going to be our 195.4 plus the 0.91. 195.4 plus 0.91. 196.31. So sometimes we'll write that interval like this, 194.49, comma, 196.31. So that's lower bound, comma, upper bound. That's a lot of times how you'll write those intervals. And now we want to interpret this result. So what we know is we know that this should be true 95% of the time for 95% of the samples. So the way that we state that is we say that we are 95% confident that the population mean, mu, is between 194.49 and 196.31. So, and that's the population mean weight. So this is the population weight. So we're 95% confident that the population weight of all American men is between 194.49 and 196.31. So we got an interval of values, and then we've got reliability attached to it. That's a confidence interval.